Okay, preface, this section is going to be long. It's going to be hard, okay? That's the warning. The warning's out of the way. This section is very cool, okay? I'm really excited to talk about this section. There's so many cool things. Video 2 especially is going to model something like the spread of diseases, which may or may not be an interesting topic at the current moment. I wish it weren't, but it is. Anyway, we're going to start with radioactive decay, something a little bit more mundane. All right. So we're going to start with an example because I love teaching with examples. So the percent P of T of carbon-14. So I'm going to interrupt myself real quick. We're going to talk about carbon-14 a lot in this section. So carbon-14 is a radioactive isotope of the element carbon, okay? And again, I'm no chemist, and you don't need to be a chemist either, but essentially what happens is it decays over time, and there's a lot of things we do with this. One of them is we can use this to date organic materials. But anyway, here's the abbreviation for carbon-14, because I don't want to write it a lot. The 14 is like an exponent that's written before the C. Okay, it's like a superscript, but it's written before the C. And this has to do with like notation of isotopes in chemistry. You can read more about it. This right here is I researched this for the video, so I wouldn't embarrass myself. It's like the weight or the total number. Yeah, I think it's the atomic mass of this specific isotope. And I was going to say the denominator, the subscript, which we don't write, but you could write a subscript of 6, is what element it is in the periodic table. Okay, it's always 6 on the bottom. Anyway, so we're going to be writing it, abbreviating like this. Again, disclaimer, I literally haven't taken a chemistry class since high school, but I did read about it so that I know. Whatever, let's go on. So the percent of carbon-14, which we're going to abbreviate like this, remaining after T years can be modeled with the following table. Okay. So what do we got? I'm going to give you a table of T's and P of T's. So to start off, right, at the very start, how much percent do we have left? Well, nothing is decayed yet, right? We haven't started yet. At the very start, we have 100%. Okay? And remember, P is the percent remaining. So if P is 100, that means we have 100%. Percent is the units here. All right, and after about 5,730 years, P is 50. Okay, so after 5,730 years, we have 50% of what we started with. After 11,460, we have 25% of what we started with. And we can keep on going. After 17,190, we have 12.5% of what we started with. Okay, it's radioactive decay. It's decaying at a constant rate. And specific notice, right? Well, I'm not going to tell you what to notice yet, because we're going to do part A. Estimate what percent is left after a total of 22,920 years. So notice what's happening, right? Every 5,730 years, we lose half of what we have left. Okay, right? In the first 5,730 years, we lost 50%. Next, we lost another 50% of what's left, right? 50% of what's left is 25%. And then we lost half of that after another 5,730 years. So after another 5,730 years, we should be at half of this. Okay, so it's going to be 6.25% of what's originally there. All right. So it's decaying at a constant rate. This is an exponential decay situation, right? Remember the whole idea about exponential decay that we talked about in a previous section in 6.1 is we can model exponential decay functions like this, where A is the starting value. In this case, our starting value would be 100. And B has to do with growth or decay. So here we keep on getting halved, so it would be 1/2. And X would be the number of periods of 5,730 years. That's a very awkward thing to say. X right here is the number of periods of this time. We have a word for that, okay? That's called the half-life. And I spoiled it for you. That was part B, okay? I'm going to ask it anyway, just to get it in your notes. All right, wait, where did that? The half-life, like, you know, it's going to be a time. The half-life of an exponentially decaying quantity is the time required for half of the quantity to decay. All right, so the question here is, what is the half-life of carbon-14? And as a very small side note, there's no like universally agreed upon half-life for carbon-14 that I have found. Different texts use different values. It's, you know, it's something that's, you know, we can't just easily measure. You may or may not believe this, but it decays pretty slowly. Carbon-14 does, right? 5,730 years is a long time for an experiment. Okay, and there are ways to get around that in general. And again, I don't want to talk about them too much because I'm no chemist. But that's why we have an approximation, really. So some books will use one number, some books will use another number, but it's about this long. Okay, so the question is, what is the half-life of this? Well, it takes 5,730 years for half of it to decay. After another 5,730 years, another half decays, and another half decays, and it keeps on getting cut in half. So that's what the half-life is. It's the time it takes for half of the things to decay. All right, we can do more problems with this. Part C. Recall that exponential decay can be modeled by A of t is equal to A naught e to the kt. And in a previous section, right, we used different letters. I think we used a P right here. I think this was an R right here. And remember we said if our rate, in this case our K, is negative, it's exponential decay. Decay. If our K value or our rate is positive, then it's exponential growth. All right. So what we've got here is a standard form for an exponential equation. Again, we can use different letters. I'm trying to be consistent with the book, and the book is not consistent with itself. But in this section, this is the equation that the book uses. Okay? The question is, find a formula for the percent left after t years. And this can be a little tricky. Okay. Let's start with the easy part. Okay. A of t, that's going to equal our starting value times e to the kt. Let's not worry about k yet. K is going to be a little tricky. But our starting value, right, we started with 100%. So if A of t is in percents, dang it, I said P of t. Well, we're switching to A of t. If A is t is percents, we start with 100%. But we need to know what K is. So the way that we're going to use K We're going to use given information to find K. So what are some things that we know? We know the half-life is 5,730 years, which means every 5,730 years, half of it's decayed. So specifically, right, we know that when T is 5730, P is 50. I think we're using A now. All right. So we know A of 5,730 years is equal to 50%. So plug that in. A of T is going to be 50. And that's going to be when T is 5730. And now we can use this to solve for K. This is an exponential equation. This is 6.6, which, depending on when you're watching this video, is either 2 weeks ago, 1 week ago, or some other time, depending on whether you took a Thanksgiving break. If you did, happy Thanksgiving. Hope you had a great time with your family. Anyway, so we need to solve this. Remember, when we solve exponential equations, we get the exponential by itself. So we need to divide by 100. So divide both sides by 100. We're going to get 50 divided by 100 is equal to 100 divided by 100. It cancels each other out. E raised to the 5730 times K. We usually write the variable second, but these exponents are the exact same thing. Once we have the exponential by itself, we undo it by taking the natural log of both sides. All right, so we're going to have the natural log of a new piece of paper. The natural log of the left-hand side was 50 over 100. That simplifies to 1/2. Equals the natural log of the right-hand side. Natural log and e to the x cancel each other out. Left-hand side, right-hand side is just left with 5730 times K. And I'm pretty sure that's the half-life I'm using today. Yeah, 5730. So now to solve for K, we just divide by the coefficient. K is going to be the natural log of 1/2 over 5730. And a lot of times you'll see this rewritten to look a little nicer. Right? The natural log of 1/2. Remember, 1/2, that's 2 to the negative first power. So by the rules of exponents and logarithms, that exponent comes out in front. We can write it as negative ln2 over 5730. This is our K value. We needed that K value because we were close to knowing the equation, but we didn't know our K. So let's plug in our K to this information and we'll have our answer for part C. Okay. So A of T was A0. We said A0 was 100, our starting value. E to the K, which is negative natural log of 2, divided by 5730 times T. This is the percent of carbon-14 that's left after T years. In general, right, to find your K value of any radioactive substance, it will always be the negative natural log of 2 divided by the half-life. Okay? If you wanted to memorize this formula, you could. I don't recommend it, but some people really like formulas. Use capital T. That's the half-life. If you're the kind of person who really likes formulas, you can use this to quickly find your K value. It can also be used for doubling time, but we're not really going to talk about that here. Okay, so 14 minutes into the first video, and we are 1/3 the way through the examples. Almost. We still have to, no, we're not even close. It's going to be a long section. Okay, but I'm trying to give you guys a lot of examples to make it a little easier. You don't have to watch the whole videos. Part D. What percent is left after 7,000 years? Also, we should know where we're going with this. 7,000 years. Remember, we were given a little information. After 5,730 years, we have 50%. After a lot more years, 25%. 7,000, right, is somewhere in between. So our answer should be somewhere between 25 and 50%. Okay? That's what we're expecting here. Let's see if it's between 25 and 50%. So we already did the hard work. We just need to find what A of 7,000 is. We're just going to use our formula. It's going to be 100 times e to the negative natural log of 2 over 5730 times 7,000. And really the hardest part for part D is just making sure that you plug it into your calculator correctly. Okay? So be very careful with your calculator. Again, I very frequently use Google as my calculator. But I highly recommend that you do not use Google while taking your exam. I think HonorLock would probably get a little upset. All right, so what have we got here? We have 100 times e raised to, make sure to have parentheses, negative natural log of 2 divided by 5730 times t, which is 7,000. And we're going to get about 42.879%. Okay. So let's say approximately equal to 42.879% as our answer. So we said it'd be somewhere between 25% and 50%, and it is between 25% and 50%. That was not as bad as the other problems. All right, let's finish off this example. When will 20% of the carbon-14 remain? And again, we have an idea of what our answer is going to look like. Here's when it's 100% left. Here's when 50% left. Here's when 25% left. The question's asking when is 20% left? Well, it's going to be a little after this time. So some number between like 12,000 and 17,000 years. A long time. All right. So we want to know, right? When is, another way of phrasing this is when is A of t equal to 20? Remember, A is given as a percent here. Otherwise, you'd have to convert it to a decimal. Well, A of t is up here. So when is A of t equal to 20? Well, when that left-hand side is equal to 20. It's going to equal 100 times e to the negative ln 2 over 5730 times t. And again, we got to solve an exponential equation. And this is going to look very familiar. Isolate the exponential. Divide both sides by 100. 20 divided by 100 is 1/5. Equals e to the right-hand side, negative ln 2 over 5730 times t. Natural log both sides. Once the exponential is by itself, we have to undo it to get to the variable. So if we natural log both sides, we'll get the natural log of 1/5 is equal the natural log of an exponential. They are inverse functions of each other, so we're just left with the exponent. Negative ln 2 over 5730. Now, all that's left is multiplying by the reciprocal. This is just a number. This is just a number times t. So if we have a fraction times t, if we multiply both sides by the reciprocal of that fraction, then t is by itself. So it'll be the natural log of 1/5 times the reciprocal will be negative 5730 over ln 2. And this is our exact answer. It could be simplified a little bit. The natural log of 1/5 is negative natural log of 5. The negatives would cancel. We can do a couple things, but we're getting approximation. So again, don't approximate until the very end. Otherwise you get compounding rounding error, which is not so good. So again, go off to your calculator and type this in. You're going to get that t is the natural log of 1/5 times negative 5730 divided by the natural log of 2. Which is about 13,305 years. And again, we said our answer should be somewhere between 12,000 years and 17,000 years. And it is. Okay? So 20% of that carbon-14 is going to be left after about 13.3 thousand years. All right. And that's the first example of the first video, 20 minutes in. I got 2 more examples for you though. You have everything you need to solve this, but these next 2 can throw a couple tricks into those homework problems. let's look at example 2. A substance has a half-life of 5.2 minutes. So the half-life for this substance, by the way, is a little bit shorter than the half-life of carbon-14. Carbon-14 took 5,730 years to decay half of it. This one, half of it goes away in 5.2 minutes. All right. So if the initial amount is 112.5 grams, part A, how many half-lives will have passed before we have 7.03125 grams left? So the whole idea of this is a conceptual understanding of what a half-life is. Half-life is the time it takes for half of this substance to decay. All right? So you're going to go to your calculator and you're going to say, okay, what do I have initially? Initially, we said we had 112.5 grams. After one half-life, we should have half of that left, 56.25. After another half-life, we get 28.125. After another half-life, we divide it by 2 again. We get that. After another half-life, we have 7.03125. Okay. So how many half-lives is that before we got to the number of grams that we thought we were going to get to? Well, 1 half-life, 2 half-lives, 4 half-lives. Okay, so that's our answer. How many half-lives? 4 half-lives. And part B is, how much time is that? How much time does that take? Well, it took 4 half-lives. How long was each half-life? Each half-life was 5.2 minutes. So it's going to be 4 times 5.2 minutes, which would be 20.8 minutes. So it got a lot smaller just in 20.8 minutes. And if you really want to be a superstar, you could convert 0.8 minutes into seconds. You could say 20 minutes and 48 seconds. All right. But I'll accept this as an answer. Okay. And that's example 2, a little shorter than example 1. So let's do example 3. Oh, there's a bit of sun. Give me a second. All right. So we're going to end this video with a doctor. All right. So a doctor prescribes 110 milligrams of a drug that decays by roughly 35% per hour. So this problem doesn't give us a half-life. It gives us a 35% life or something. That's not a term, okay? But we know in an hour, instead of, well, not that in an hour we lose half of it. In an hour, we lose 35% of this, okay? So we're going to ask some questions. Model this with y is equal to a times b to the x. So remember, 6.1, A is the starting value. Starting value is 110 milligrams. B is what you multiply by to get your growth or your decay. It's going to be 110 times something to the x. It's not 35%, right? If it decays by 35%, then how much do you have? Right? If you lose 35%, that means you have 65%. Okay? So this is going to be 0.65 right here. And we can model this way. Y equals 110 times 0.65 to the x power. But for a variety of reasons, we don't like models like this. Okay? And again, we know this is decay because our B value is less than 1. Mathematicians don't like models in this form. We like models that have e to the x. We like models with e. And there's a lot of reasons for that. One of the main ones is that everything with calculus for e to the x is so much simpler. Okay? It's so much nicer to deal with derivatives and integrals and all of the stuff when you deal with e to the x. And there are some other reasons as well. Okay? So that's our answer for part A. So part B says model this with our new formula. All right, A of t is equal to A naught e to the kt. Now there are two ways of doing this. Okay, the first way is to do what we did in example 1. A naught, that's our starting value, 110. And we could use a point to find out and solve for k. And that's probably what I'd recommend. Solve this like we did 1 part B. Okay, look back to 1 part B if you don't remember. But for here, there's another way of doing this. Right? We can rewrite 0.65 to the x as e to the kt. And this is the trick. Don't expect you to see the trick, but I'm going to tell it to you, and hopefully it'll make sense. Would you agree that 0.5 to the x is equal to e to the natural log of 0.65 to the x? It looks a bit weird, but it's true. These are inverse functions of each other. E to the natural log, they cancel out. We're just left with 0.65, which is exactly what we had. So notice, while we have an exponent raised to an exponent, we can multiply those together. This is going to be e to the natural log of 0.65 times x, right? Exponent to an exponent, you multiply those exponents together. And our a naught is the same as before. So we're going to say that a of t is equal to our starting value, which is a naught, 110, times e to our k value is natural log of 0.65. Oh, and we should be using the right variable. Our variable here is t. So this is one way, and this is a trick you can use to rewrite something b to the x as e to the kt. All right? It's a trick. You can also do this just like we did 1b. So go back and look at 1b if you don't like this method, or you can use this method. All right, 2 more, and then we're going to be done with this 30+ long minute video. Part C. What is the half-life of the drug? And again, we should know what kind of number we're expecting, because we know it decays by 35% every hour. So in a single hour, we lose 35%, which means it's going to take more than an hour to lose 50%. So So our half-life should be more than an hour. Okay. If we get our half-life is less than an hour, we probably did something wrong. It's only decaying by 35% in an hour. Half-life is how long does it take to decay 50%, which is, of course, more than 35%. All right. And then, yeah, depending on your mental math abilities, you can actually get a pretty good estimate in your head. We're going to do this by hand. Remember, half-life is when is half remaining. We're going to say when is half remaining. Well, we started with 110, so that's when is 55 milligrams remaining. Well, we're going to plug in 55 over here. It's equal to 110 times e to the natural log of 0.65 times t, and we're curious about t. We get to solve another exponential equation. Divide both sides by 110. 55 divided by 110 will be a half, or it better should better be a half. That's why we chose 55. Is equal to the e to the natural log of 0.65 times t. Be very careful. These don't cancel right here because the t is not in the natural log. It's only e to the natural log of something cancels, but there's something else going on in the exponent. So we take the natural log of both sides. Left-hand side is the natural log of 1/2. Right-hand side, the natural log of e to the x, cancels each other out. We're just left with the exponent on the right-hand side. And again, this is just a number. A number times t, divide by that number, and we'll have our answer. The natural log of 1/2, which again could be simplified, divided by the natural log of 0.65. This could be simplified, but we're just trying to get an approximate idea of the half-life. We're going to approximate it right here. So type that into our calculator. The natural log of 1/2 divided by the natural log of 0.65. That's going to be 1.609 approximately. So we said it should be more than an hour. And we got this many hours. And again, I'm going to be fairly lenient. It's almost the end of it is the end of the semester. This is your last section. I'll take this as an answer. Writing it with minutes is a little bit more useful. That's going to be an hour. And what is 0.609 hours in minutes? You multiply it by 60. This is going to be about an hour and 37 minutes. Is another way to write your answer over here. All right. Last problem, part D. And then we'll be done with this video. So part D asks, find A of 10 and interpret. So all we have to do is plug it in. We have that A of 10 is equal to our initial value, which was 110, times e to the k, which we said was the natural log of 0.65, times t, which is 10 here. Plug that into a calculator and see what we get. All right, so you plug it in, you get 110 times e raised to the natural log of 0.65 times 10. You're going to get 1.481 approximately. So, did I type this in correctly? Does this make sense? Did I use the right function? I'm a little nervous. Our function was 110 e to the ln of 0.65 times t. Great. What are our units for our amount? It's milligrams. Exponential decay is fast. That's why I'm shocked. So we started with 110 milligrams. This says after 10 hours. After 10 hours, we only have 1.481 milligrams of the drug in our bloodstream or wherever it is. All right. And you can see this, right? We started with 110 milligrams, and every hour we multiply by 0.65. Every hour we lose 35%, right? So after 1 hour, you have 71 milligrams. After 2 hours, 46 milligrams. Then 30 milligrams after another hour, then 20 milligrams, etc., all the way until 10 hours is going to be 1.48 milligrams. Okay? So there's a lot of stuff here with exponential decay. I wanted to give you more examples rather than fewer examples. I hope I don't overwhelm you. Hopefully this helps. We also are going to be talking about logistic growth, which is used to model the spread of diseases, as well as gated populations. We also, I'm not talking about like gated apartment complexes or whatever. We're also going to be talking about Newton's law of cooling, which will be pretty quick, and logarithmic scales, which are pretty quick. So 2 long videos, 2 short videos. Good luck.